A whole lot of chemical reactions result in gas mixtures. So now that we know the ideal gas law and we know Dalton's law, we need to put those things together so that we can learn about total pressures in reaction mixtures. Here's a simple example, right? We've got several compounds and all of these are gaseous. Phosphorus pentachloride is a gas, phosphorus trichloride, and chlorine. And if I wanted to write a balanced chemical equation for that, this is a good practice for naming covalent compounds and a good review. Phosphorus pentachloride, PCl5. Phosphorus trichloride, PCl3. And chlorine, Cl2. It's said in the problem that they're all 1-to-1, so that all these coefficients are 1, but I hope that you could figure out by looking at it that it was already balanced. There's 1 phosphorus and 5 chlorines on each side. Now, when I make gases, I'm less concerned about the mass of the gas that I'm going to make because I'm not like collecting it settled. I'm collecting it in a container. I want to know how much volume I'm going to make so that if I'm designing an experiment, I design a container that's big enough and strong enough to hold whatever gas I make without breaking. And so I do problems like this, right? I need to assume that at the end of this problem, after all the reaction has happened, the total pressure is going to be the sum of any phosphorus pentachloride that's left, phosphorus trichloride, and just chlorine gas. So whatever gases are left are going to contribute to the total pressure. Well, I've got stoichiometry information, don't I? My strategy is going to be stoichiometry to get moles of PCl5, PCl3, and Cl2. And then PV equals nRT to get pressure. And there's a couple of strategies we can use for that. We'll get there in just a second. But before we do that, I want you to notice that the phosphorus pentachloride is fully decomposed. That means complete reaction. In other words, no PCl5 left. So when this equation is all done, when this math is all done and when we've all finished, there's not going to be any phosphorus pentachloride to contribute because it all reacted away. I'm going to be focusing on phosphorus trichloride and chlorine gas. So let's see if we can do that stoichiometry first. Pause and use the information that you were given to figure out how many moles of PCl3 and moles of Cl2 that you can make. This is not a gas law problem yet. Go back to your early Gen Chem stuff and just do stoichiometry. Okay, remember stoichiometry in this case is just about taking the mass of the reactant and converting it to moles, and then going from the moles of the reactant to the moles of the product. And when you do that, you get 0.251 moles of PCl3. Now, I could do this whole stoichiometry problem again, replacing the ratio of PCl5 and Cl2. But it's also 1-to-1. So why am I going to waste my time doing that calculation when I can say, well, if I made 0.251 moles of phosphorus trichloride, I am also going to make 0.251 moles of Cl2. So that's our first step, stoichiometry to moles. Now, PV equals nRT to get pressure. Here's what I want you to recognize. In the previous video about gas mixtures, we found all the components individually. We did 3 PV equals nRTs on that can of compressed gas, and we added up the pressures. Well, Dalton's law could let us do that, or we could also recognize, and this is also just simple math, that adding the moles together gets the total moles. And I could say that the total pressure is equal to times V on the left side of the equation. The total pressure is just equal to the total moles times R times T. So I'm solving for P total. The total moles is just adding these two things together. So 0.502 moles. We know R as a constant, 0.08206 liter atmospheres per mole Kelvin. I don't see a container temperature. So we're going to assume, right? If I'm not told, assume 298. That's a pretty standard assumption. So we're going to use 298 Kelvin because nobody told us, we assume. And then the volume was given, 2.5 liters. So now we just solved. So one ideal gas law problem got us where we needed to go. 0.502 times 0.08206 times 298 divided by 2.5. The total pressure in here is 4.91 atmospheres. Right, so Dalton's law says we could either find all the pressures individually with a bunch of little ideal gas laws, or we could just add all the moles together and use the ideal gas law once, right? But in any case, when there's a mixture, the stoichiometry has to feed into the idea of adding together the components of the mixture and some way of finding total pressure. Another thing to think about is that pretty much every reaction you do technically results in a gas mixture when it takes place over water. So if I scan through this problem, what I see is we're reacting solutions with solids and we're making a gas. And so, you know, if I was thinking about what this would look like in my head, I'm thinking about a beaker and I'm thinking about my zinc solid sitting on the bottom. And I'm thinking about solution above it, which is a whole lot of water, right? H2O and HCl. That's what an aqueous solution of HCl is. And, you know, if I wanted to catch that gas at the end, I could use a balloon. I could hook it up to the top of my container. And in that balloon is certainly the H2 gas, right? Gas rises and it's going up. But the thing is, and we already talked about this earlier in the semester, anytime I have a closed container with liquid in it, I have gas particles over top of it, right? So this is a closed container. It's just the balloon is closed, the beaker is closed. So I have to take into account the vapor pressure, right? Because remember, vapor pressure was the fact that I had gas particles and they were exerting a pressure. And so, you know, in this container that's filled with gas, some of it is my H2 product, but some of it is water vapor. So I always have a mixture. And so my total pressure is just the pressure of the H2 that I made plus the water vapor that's there because there was water in the reaction. And so, you know, I see that I'm collecting at a total pressure of 760 millimeters of mercury. So 760 millimeters of mercury is equal to the pressure of H2 plus the pressure of H2O. And because this is such a common occurrence, people have looked at this and they've made tables. And so what I want to show you is a table in your textbook that is in chapter 9. And so you see in this chapter, in this textbook, there's the vapor pressure of ice and water in various temperatures. What that just means is I've got a closed container and it's either got water in it with vapor over it, or it's got a block of ice in it and there's always gas over it. And so people have measured at different temperatures what it is. And so when I look back at my problem, right, back in my problem, I had .30 degrees Celsius. And so I simply look it up. I go into my table. Where are we? There we go. I go into my table and I say, oh, 30 degrees Celsius. Well, apparently 31.8 torr of my gas mixture was water. And so I go and I take care of that. So let's go back into our problem here. Right? We had said that P total was the pressure of whatever H2 I make plus the pressure of the water. And we had said that the total pressure was 760 millimeters of mercury. And now I have my 31.8 millimeters of Hg. So whatever the H2 is, it's just a subtraction problem, all right? 760 minus the pressure I got out of the table, 31.8 in this case, right? So this is pH2O at 30 degrees Celsius, 728.2 millimeters of mercury. And of course, I really don't usually keep things in millimeters of mercury. I might as well just go ahead and convert it to atmospheres in case I need it later. So 0.958 atmospheres of H2. So if that's the case, we wanted to know the volume of H2 inside the container, right? Well, I don't quite know yet because I have PV equals nRT. Well, I've got a P, right? That's 0.958 atmosphere. I've got a volume I'm solving for. I've got an R, and I've got a temperature, right? We said that that was 30 degrees, so that's going to be 303 Kelvin. I don't have moles yet, but I have stoichiometry, right? I can use stoichiometry to say, well, if I start with this much zinc, I get this much water out, or sorry, this much H2 out at the end. Let's go ahead and do that. It looks like if I use the molar mass of zinc to turn that 1 gram into moles, and then I use the coefficients from the chemical equation to go from zinc to H2, I made 0.0153 moles of H2. And so that is what I can go put into my PV equals nRT problem. And now I can solve for the volume. So 0.0153 times R, which is 0.08206 liter atmosphere per mole Kelvin, times 303 Kelvin, divided by 0.958 atmosphere. The volume is 0.397 liters, or if I felt like converting, 397 milliliters. So there's kind of two parts that I have to think of. This is called gas collection over water. So sometimes in problems, you'll see something like the gas was collected over water at a temperature, right? Well, what we have to remember is I have a certain pressure and I have to subtract out how much of it was water. And then stoichiometry, plain old stoichiometry back from the very beginning of the semester, will get me moles. Putting those together with PV equals nRT will get me other things that I might like to know, like volumes or temperatures.